This the light that's gonna illuminate the way we moving. Trust in me, we going God mode, the theory's proven. Light 'em up, beam me up, the only GOAT, the genius one. They switching sides, I seen it coming. The plot twist, a convenient one.
What's up, guys? It's been a minute. Welcome back to Quantum Pinguino. Today's topic is a phenomenon called false vacuums. However, before we can delve deeper into that, we need to first have a small review of the Higgs potential. In its simplest form, the Higgs potential is a function of a complex scalar field phi, where it has both a quadratic term and a quartic term. The quadratic term, mu squared, is often called the mass squared parameter, or Higgs mass term. On the other hand, the quartic term lambda is called the self-coupling, which we assume is positive, aka lambda greater than 0, so that the potential is bounded at positive infinity as the absolute value of the scalar field phi goes to infinity. For the sake of argument, even though mu and lambda both have values that have been determined by experiment, let's just assume that lambda is 1 and that mu squared can be either plus or minus 4. In the first case, when mu squared is greater than 0 and it's equal to 4, the potential has a single global minimum at phi equals 0. In this case, there is no spontaneous symmetry breaking, so the electroweak gauge bosons, the W and the Z, remain massless. However, this prediction has been ruled out by experiment. In 1983, Carlo Rubbia and Simon van der Meer's teams at CERN's UA1 and UA2 experiments observed W and Z bosons with masses around 80 and 90 GeV respectively, demonstrating that mu squared cannot be positive. In the plot shown from the CERN UA1 experiment, we see on the x-axis plotted the reconstructed mass of electron-positron pairs. In the low mass regime, we see contributions from quantum chromodynamics, or QCD, while in the high mass regime, around 90 GeV, we see what's a very coarse reconstruction of the Z mass. This disproves the idea that mu squared is positive, as we have seen evidence of symmetry breaking, which is the process by which the W and Z bosons gain their mass. Now let's consider the other case where mu squared is less than 0. When we flip the sign, we see that we now have a local maximum at phi equals 0. This local maximum is unstable, meaning that small deviations about this maximum lead to a cascading fall in the potential. Around this relative maximum at phi equals 0 are a circular set of degenerate minima that can be found at the absolute value of phi equals the square root of negative mu squared over 2 lambda. You can find this value simply by deriving the potential with respect to the absolute value of phi and setting it equal to 0. The idea of spontaneous symmetry breaking comes from the fact that basically any direction you go to from this phi equals 0 local maximum gives you a absolute minimum that is degenerate in energy with respect to all the other minima. So the direction that you actually fall towards doesn't end up mattering in the end. Once you're at one of these minima, these small fluctuations both radially and tangentially to the circle of degenerate ground states is what actually gives rise to the Higgs mass and the W and Z boson masses. The radial fluctuations are what gives rise to the Higgs mass, while the tangential fluctuations are what is called Goldstone boson modes that are consumed by the W and Z gauge fields, giving rise to the W and Z masses. So now we're ready to talk about what a false vacuum is. To do so, we'll use a bit of a toy model, which uses the double well to express this concept. First, we have the symmetric double well, which has 2 degenerate minima at plus or minus phi equals 1. So these are both true vacuums, just like the ring of the minima in the Mexican hat potential belonging to the Higgs. Whether you kick the field a bit or even rely on quantum tunneling, you always end up in one of these two equivalent lowest energy states. However, let's add a slight kick to the double well potential with this extra epsilon phi term, where epsilon is some small positive value. Now the left and right wells sit at different depths. The shallower one, at phi equals plus 1, is only a local minima, or what we refer to as a false vacuum. Small fluctuations will keep you there, but a large enough shove, or even quantum tunneling, can carry you over this potential barrier into the true vacuum at phi equals negative 1. This simple 1D picture shows exactly what I mean by a false vacuum. It looks like a stable minimum, however it isn't the global minimum, and eventually the field can fall through to this lower energy state. So how does this tie back to the Higgs Mexican hat potential that we were discussing earlier? Well, I was keeping a little bit of a secret from you guys, which is that the Mexican hat potential of these degenerate vacuum states is only valid to first order. Once we start including high order loop corrections to Feynman diagrams, this is not quite the case anymore. As an example, let's consider the one loop correction to the Higgs self-coupling through a top quark loop. This has the highest effect on the Higgs potential due to the fact that the top quark is the particle of the highest mass that couples to the Higgs, meaning that it has the highest Yukawa coupling. Once we introduce the correction into the Higgs potential that accounts for this Higgs self-coupling top quark single loop, we see that we have now this extra term which looks a bit nasty, and it's a function of the Yukawa coupling YT, which is directly proportional to the top quark mass, phi, the complex scalar field, and also mu r, which represents the renormalization scale, which is an arbitrary energy scale at which you define your running couplings. In practice, this is often going to be on the order of phi. If you look closely, this is basically exactly what we have when we have the asymmetric double well potential. This extra correction for the top quark loop is effectively the extra epsilon phi term that we had when we tilted our double well potential. What this means is that in reality, the Higgs potential is tilted, and the vacuum energy state that we're currently in is what's called metastable, or a false vacuum. This implies that a true vacuum does exist, and if you imagine that a tiny bubble of true vacuum forms somewhere in the cosmos, triggered by quantum tunneling or another rare fluctuation, this bubble would cause the Higgs field to settle into a lower energy state, incompatible with the physics that we know. This bubble will then race outwards at the speed of light, converting everything in its path into this true vacuum state with no warning, no shockwave, and no radiation to see it coming. Although studies have shown that the chance of this happening exceeds the lifetime of our universe, if it ever did occur, we'd be wiped out in an instant and we'd never know what hit us. And with that, I'll leave you with something to keep you up at night. If you're interested in learning more, please look up the literature on bubble nucleation or instantons. But that's all from me. Thanks for watching. This is Quantum Pinguino, and I'll see you next time.